Good afternoon, everyone. I'm Rebecca Hartley, the Director of Operations for the Center for Workforce Development and CAVES through our NSF ATE grant and center. Just want to do a quick introduction and give just a couple of housekeeping items. The first is if everybody could mute their laptops and computers just so we can make sure we can hear. And let us know if you have trouble finding that button. It should be by your name on the right side of the screen. Okay. Yeah, just everybody take just a moment to mute your speakers. Okay, great. Thank you. Well, this is our second webinar with virtual reality. And so if you joined us last time, you remember that we were focused on machine learning and kind of gave you an introduction of machine learning with Dr. Jerome McClendon from Clemson. Today, we're going to focus specifically on virtual reality. And we have another Clemson faculty member, Dr. Babu, who is an associate professor in the Division of Human-Centered Computing in the School of Computing at Clemson. Dr. Babu received his BS in 2000, and MS and PhD degrees from the University of North Carolina at Charlotte. And he also completed his postdoc fellowship in the Department of Computer Science at the University of Iowa. He joined Clemson in 2010, and just about that time is when he started working with the Center for Workforce Development and helped us with a pipeline of graduate students that could help us with the development of a lot of the virtual reality modules or simulations that you see. So his students have helped with a significant portion of research that has helped not only his team, but our team make sure that the modules that we are developing really complement the curriculum and what we're hoping that you're using some of our partners in your own classrooms. So his research interests are in the areas of virtual environments, virtual humans, applied perception, educational virtual reality, and 3D human-computer interaction. He's authored or co-authored over 75 peer-reviewed publications in premier venues in this research field, and his work has received over 1,000 citations. He was the general chair of the IEEE International Conference on Virtual Reality in 2016. He also served as the program co-chair for IEEE VR in 2017. He and his students have received 5 Best Paper Awards in venues such as the IEEE International Conference on Virtual Reality and the IEEE International Conference on 3D User Interaction, the ACM Symposium on Applied Perception, and the IEEE International Conference on Healthcare Informatics. His research has been sponsored by the U.S. National Science Foundation, the U.S. Department of Labor, and locally St. Francis and Medline Medical Foundations. So you can see Dr. Babu is very well published. He's very well known in this field. And so we have asked him to present to you 3 research studies that he has conducted in this virtual reality space, and to give you a broader view of how this is impacting student education as well as industry needs. So I'm going to turn it over to Dr. Babu and let him get started. And then at the end, we'll have some time for Q&A, and you can do that in your chat window below. My colleague Zach has already put a couple of notes in there. And so as questions come up that you think of during the presentation, go ahead and type them in, and then Zach or I can help to get those to Dr. Babu at the end of the presentation. So Dr. Babu, I'll turn it over to you now.
Hi, everyone. I hope you all can hear me. All right. So I would thank you for this wonderful introduction, Dr. Hartley. And also thank you, Zachary, for helping me moderate this talk today. So without further ado, let me jump right in. So here is a picture of my research group. So I chair the Virtual Environments Research Group on the Clemson campus. And my co-directors are Larry Hodges and Andrew Robb, two other faculty members in the School of Computing that do VR research. The work that I'm presenting today is done with the assistance of many of my graduate students, as well as my collaborators who come from a variety of different departments, such as psychology, industrial engineering, as well as automotive engineering. These are pictures from my research group. We have a very social research group with 20+ students that are partly undergraduate students as well as graduate students. And we conduct a lot of studies in the virtual reality realm, as well as develop lots of new simulations for a variety of different fields, such as automotive and aviation technical education, as well as healthcare domain. So we have one foot in research, so to speak, and another foot in computing system design and development. So one of the three projects that I'm going to be talking about, the first one of which is on the design and evaluation of a VR simulation testbed for the evaluation of autonomous vehicle algorithms. So the three research directions I'm presenting today are all very new research directions that we have had some success in publishing. So this work was published in the SAE conference in 2019. So working with automotive engineering folks, as well as network science researchers in the School of Computing, we have developed a unique platform that basically emulates the functions of futuristic autonomous vehicles. So autonomous vehicle systems are currently evolving in terms of their engineering. Their sensors that are fitted into autonomous vehicles are doing more interesting things than ever before, and more sensors are being fitted into vehicles, and they need to be tested in a safe and effective manner without putting real pedestrians in danger when they're tested in physical environments. So we have created a VR platform that provides a safe and effective training environment, or a test bed, so to speak, for autonomous vehicle behavior algorithms that are being developed by automotive engineers as well as computer scientists. So how can we efficiently test them? Testing in real life sometimes can be very impractical, and they're cost prohibitive because you may have to physically prototype the autonomous vehicles. And what we have worked on in the past 3 years is to create a virtual reality testing framework in which these complex scenarios in which the autonomous vehicle behavior algorithms need to be tested can be recreated and validated. And there is no risk to real pedestrians or other drivers in real roadways. And it's a very low-cost alternative to testing in the real world. So some of the key challenges for us is the items that are listed in blue here. And you can see some screenshots of our autonomous vehicle simulation, both in the real world with regards to how participants perceive the stimuli of the autonomous vehicle ridership through a VR head-mounted display. And also on the top, you see a screenshot of what they see in the virtual environment. So the challenges for us from a technical perspective is that there should be very minimal latency with regards to how the simulated autonomous vehicle in virtual reality responds to sensory inputs that it is perceiving. And then it should also be able to provide a platform for the real-time evaluation of the ridership, and real-world scenarios must be provided with high fidelity and realism. And it should be a very controllable test bed where we can, in a modular fashion, add new sensors that automotive engineers are thinking about including in the next generation autonomous vehicles, and to test them out in the virtual world. So as a initial version of this testbed, we have integrated sensors such as lane position keeping, distance to the front of the vehicle, maintaining, and also maintaining the speed of the with respect to the car ahead. So these sort of lane keeping as well as collision avoidance kind of reactions that are common in current semi-autonomous vehicles. And then also with regards to sensors that allow the vehicle's computing system to keep a map of the roadway as well as where the vehicle is located from a global perspective with respect to the road network. And then they all are fed into a control strategy, and we have a module in which automotive engineers can design these control strategies and then infuse those control strategies in there, and then we can test them with the different scenarios in the virtual world. And so things like steering, wheel directionality, acceleration, braking, all of those things can be tested. And then the rider of the virtual autonomous vehicle also has some pedals and certain inputs with which they can also interfere with the vehicle's performance. So if they need to step on the pedal, for example, then the autonomous vehicle simulation also takes that into account and then infuses those behaviors in the VR simulation in real time. One of the key things that we are also doing here is, as I said before, we are seeing more and more the infusion of many more new sensors into future autonomous vehicles. And so we need a way by which we can test these sensors. So in the VR platform, we are testing sensors with, that are lane keeping sensors, collision avoidance sensors, and as well as, for instance, sensors that may need to operate with regards to knowing the vehicle's current acceleration velocity and providing a comfortable riding experience for the user. And so the sensor emulation is one of the major contributions of this particular framework. The framework, as a result, is very complex, integrates a lot of different platforms such as Unity 3D, CarSim, Simulink, and DSRC. These are all technologies that are integrated together to create a real-time experience. In order to test this simulation for the first time, what we did was to test the adaptive cruise control aspect of autonomous vehicle behaviors that are being developed by our partners in automotive engineering here at Clemson. We actually created a replica, a virtual reality replica of the Clemson campus, and especially a high-fidelity replica of the perimeter road network of the Clemson campus. So in it, we can actually track real-world vehicles, and we use a network system that consists of multiple what's called RSUs. These are technologies that allow us to broadcast the GPS positions that are detected from real-world vehicles into our simulation testbed. And in the context of how real-world vehicles behave, surrounding a virtual vehicle that is introduced into the simulated real-world road network, we can then test how effective the new autonomous cruise control algorithm is reacting to the behavior of the real-world vehicles. So we actually are able to, in what is called a vehicle-in-the-loop system, integrate real-world vehicle behaviors in our autonomous vehicle simulation. So here is a screenshot of the perimeter road network as it is recreated in virtual reality. And we have ensured that it is a one-to-one replica. And from the perimeter road network, we are able to essentially recreate the buildings as well as the road sizes, the lane widths, for example, so that all of that is highly realistic, in which the adaptive cruise control algorithm can be in high fidelity tested. And also, we haven't done this yet, but one of our goals is also to test these algorithms in virtual reality with different weather types of phenomena. It is quite well known that the sensors on modern vehicles, on contemporary vehicles like right now with regard to lane keeping, do not work very well when there's a heavy rain because the sensors subsystems are not able to pick up the extent of the roadway. So we can test all of that with regard to sensor emulation and then sensor fidelity in virtual reality. So here's again a short video on the right that you will see, where you're essentially driving through one small portion of the perimeter road network of the Clemson campus, in which this vehicle is completely driven through the autonomous vehicle behavior algorithms that is generating its motion. And then the interior of the autonomous vehicles can also be designed in such a way that we could also test some of the human-computer interaction aspects and design new interaction metaphors in future autonomous vehicles between the occupants and those autonomous vehicles. So that's also a possibility for our work. So, and future work involves these directions here. We are trying to test a platoon formation with real-world vehicles that are introduced into our simulation in real time from the real-world networks that have our network systems that are tracking the real-world vehicles infused into the virtual world. And then in a platoon-type situation, where a virtual vehicle is also introduced in the midst of that platoon formation of real-world vehicles, we want to test the effectiveness of these autonomous vehicle behavior algorithms. We have also done some recent research using this framework to test users' cyber sickness. Cyber sickness is one of the key impediments to virtual reality, especially to virtual reality adoption in users. And so using this driving simulation, we have conducted a study in which we are testing 3 different types of situations in which the occupant is able to drive the vehicle versus, and here's the driving condition as a video. We're also able to test a autonomous vehicle condition of the road network of, this is the simulated road network of Atlanta. And in the here is the passenger condition in which the occupant is in an autonomous vehicle. And the behaviors of the autonomous vehicle, such as lane keeping, acceleration, deceleration, maintaining constant velocity, is all determined by autonomous vehicle behavior algorithms created in collaboration with automotive engineers. So we actually found through a user study that participants, when they were in the driving condition, got more cyber sick as compared to participants in the autonomous vehicle condition. It's good news for the autonomous vehicle platform. However, this is sort of contradictory to what we know about motion sickness in the real world. And so we are trying to find out why this is the case in VR in future work. Okay. The next work that I want to quickly introduce is a system that we built called iVRNote, and this was published at IEEE VR 2019 this past year. And this note-taking system is essentially a system that was created for future VR learning environments, especially collaborative VR learning environments, in which VR could be used as a online remote learning platform. And when it is used in that manner, we need a system by which students can take notes as they are viewing videos of video lectures of complex phenomena. And so we created a novel note-taking system for future classrooms, VR classrooms. So with regard to the use of virtual reality as remote classrooms, this is an idea that has been in the design phase for some time, and it has the potential to transform learning from for students to be able to provide a fully immersive system in which they could participate and feel like they're really in a classroom environment among their peers, and perhaps with the presence of an instructor, and also to be able to view lectures and to take notes. And so we want to be able to transform students from their homes to in a telepresent classroom along with their peers, and be able to provide all the facilities that are important for learning, and the most important of which is note-taking. So the requirements for the note-taking interaction metaphor is to provide support for students that have problems in understanding learning material, provide visibility of a stylus and other accessories with which they can take notes, and enable effective note-taking on a notepad, as well as some correction and post-editing types of interactions. And what is also true nowadays is that contemporary students often take pictures of some of the lecture material that is presented to them, and they may then use those pictures and incorporate those pictures into their notes. So we want to be able to provide a way of doing that in VR as well. But to do all that, we need to be able to track the pose of the participant. And so we are using a computer vision-based motion tracking system like the Connect to track the participant's pose. So at any time, using just natural poses, such as raising their hand to stop the lecture and to ask questions, for example, they should be able to interact in a similar manner in the virtual world as well. So remote participants also have a representation in the virtual classroom via what's called a self-avatar. So on the far right side, you see an image of the self-avatar of another remote student that's able to participate through telepresence in this VR classroom. With regard to a writing interface, one of the best hardwares that we found would be very helpful to use for note-taking in virtual reality is really the Wacom tablet and its stylus. But we had difficulty just directly integrating it. So the Wacom tablet stylus had to be pasted with some IR reflective tape, and we have created some computer vision or image processing algorithms with which we can very accurately track the pose, the orientation, and the position of this stylus, so that when it is in air versus when it's on the surface of the Wacom tablet, we can exactly track its orientation and its position. So on the right, you see the user interaction metaphor that we created with which participants could take notes in virtual reality and to store them. And every single keystroke is also stored in our virtual reality system so that you can revisit your notes at any time. So Leap Motion controller is used for the IR camera in the scene, and this is just an off-the-shelf controller that can be added on to the HTC Vive head-mounted displays. So here you see a participant in the real world on the left using the stylus and the note-taking system in virtual reality. And on the right, you see the virtual reality classroom with the stylus. So at any time, you can pause the lecture by just raising your hand, and that is detected by a Connect sensor. And then when you perform an OK gesture, and the OK gesture is shown on the right side, then the lecture will continue. And if you have an instructor in the scene, the virtual instructor will also continue providing the lecture. So from one stylus, from one physical stylus, whose representation in the virtual world might be a pen, we also wanted to include many different types of representations of that stylus. So the stylus could become an eraser, a timeline controller, a highlighting marker, a glue stick, or essentially a cut and paste type of tool. So all of this can be facilitated in our note-taking interface via this button on the stylus. So as you click on the button, it'll basically toggle through some of these options. So students may be distracted at any given time or have difficulty focusing on their topic. So when they take notes, for example, we want to be able to provide a control to essentially seamlessly control the timeline of the lecture so that they can see what their notes corresponded to, which particular time instance in the video lecture their notes corresponded to. So this particular interface is very helpful. Let me show you a quick video of a demonstration of this timeline control mechanism. So here's on the top on the top left, you see a view of the participant in the real world. And in the virtual world, they're in a VR classroom among remote peers who are represented as self-avatars, and they can socially interact with them, such as say hi, for instance, with their virtual classmates. And then you can see here on the screen, there's actually a video lecture that's going to play out very soon. The video lecture is on a history topic regarding archaeology in the ancient Near East and history and Egypt. And so using the note-taking interface that is facilitated via the Wacom tablet and its stylus, we have created a novel system by which participants can just seamlessly take notes in this interface. And then you can see here the clarity of the note-taking is evidence that participants have the ability to perform fine motor actions of note-taking in VR. That's one of the contributions we have made. They just slide with their non-dominant hand on top of the Wacom interface. We detect that motion, and then they can actually advance to the next page. And they can see, using the timeline function, they can advance to some other location in the video lecture and then take notes pertaining to that location as well. Okay, post-editing, we need to have an interface that will allow for post-editing. So the box cutter like interface is a nice sort of intuitive interface with which they can sort of circle any portion of their notes, and then they could drag and drop those notes anywhere else that they want, and then finally they can continue inserting some new notes with regards to the lecture that they're experiencing at this time. Note-taking by photography is facilitated through a gesture. So many students take notes with photographs in class, and they add comments and annotations with pictures in their notebook. So you can switch from a pen to a glue stick in our interaction metaphor, and then by pinching the thumbs and the forefingers to define a rectangular area in 3D space, you can use that rectangular area to essentially take a picture of the lecture material, and then you can add it to your notes. So here's a video demonstration of the same, where here in this case, you can see on the top left, first the glue stick is evoked, and then the participant makes a gesture to capture a portion of the lecture. And then using the glue stick, the student then defines an area in their notebook where that picture needs to be inserted. And then as soon as the area is defined, then the picture is automatically added to their notes. And students may also have encounter difficult words or terms from their video lectures. So we also want to be able to facilitate a speech-based AI system that is connected to Wikipedia in such a way that students could essentially, using this online encyclopedia, look up difficult words or concepts that they are unfamiliar with. So here's an video example of the same. So the student essentially utters a specific word, and then it is automatically in our system. There's a small AI module that does speech recognition, connects to Wikipedia, and then through just a screen, and this is a physical screen in the real world that does not have any imagery on it, but essentially it provides a tactile interface with which participants can scroll up and down. And their scrolling behavior or gestures are essentially recognized through the Connect interface, and they're able to scroll the relevant pages pertaining to the keyword that they do not understand. They can also, we have also provided an interface with which they can review selected notes. So sometimes the notes themselves can be confusing or too brief when they review the notes later on. So it's nice to have the video lecture play at the exact time step when the note was taken, so that they can revisit that portion of the lecture. So we have created a novel interaction metaphor in which through a highlighter interface in the virtual world, participants can essentially highlight a portion of their notes. And when they highlight that particular portion of the notes, then the system essentially shows the video lecture that pertains to that segment of their notes. So now at a different time step in the video lecture, they're taking a different segment of notes here. And now using the highlighting functionality, they can essentially highlight a specific sentence and in their notes, and the video lecture is automatically reverted to the time instance that pertains to that note, or advanced downstream to another time instance pertaining to another note segment. So we conducted a user evaluation of our system in a research study, and our key research question was to what extent the VR classroom with our note-taking system was effective, user-friendly, engaging, and satisfying as compared to a physical learning environment. And we used best existing online learning environments as the other condition. So the online learning environment consisted of WebEx, as well as some digital note-taking tools, just simply a note-taking interface on a touchscreen system, such as an iPad with a stylus, and WebEx on a screen. And so we had 10 pairs of participants that were recruited. Essentially, the pairs of participants were present in both the real world as well as the online learning system together. And their ages range from 21 to 27 years old, and they were recruited by at a partnering university. So the study involved a 2x2 system design in which participants either participated in one session in the online learning system in a specific topic, such as a science topic, such as metrology, or a humanities topic, or history. And so we wanted to study, and then on another session, they participated in the other condition. So if they were in the online learning session on day one, when they came back 2 days later, then they were essentially in the virtual reality condition, and vice versa. And we wanted to test in our user study how well participants learned the material in 2 different domains, both in the humanities as well as in the sciences. So with regard to learning effectiveness, what we actually found in a difference between pre and post test with regard to learning effectiveness of both the science as well as the humanities topic, the virtual reality system performed in an equivalent fashion as compared to the online learning environment. So participants were able to learn the material just as effectively using our system as they did in the online learning environment. However, with regards to how motivating the learning environment was, or how effective the learning environment was with regard to overcoming challenges in terms of learning, and also with regards to what extent participants were able to focus on the materials when they were using the VR system as compared to the online learning environment, or how satisfying it was. In all these 4 dimensions, we found that participants in the VR condition scored significantly higher than participants in the online learning environment condition. And so they found that they could focus on the materials effectively. They felt more motivated to learn the materials, and it helped them sort of overcome certain challenges such as distraction when they were using the VR system, because they could not see a lot of the other cues that could distract them in the real world. So when we also looked at the writing performance with regard to the notes that participants took, we found that the size of the notes that they took was much larger in the virtual world as compared to the real world. And we are looking at the motor control aspects of how writing and art is different in the virtual reality world as compared to the real world in some future studies that we are doing right now. Okay, so this was a joint work with Clemson professors as well as faculty members and students at National Chiao Tung University in Taiwan. This is an international collaborative effort that resulted in this new system. The last bit that I want to talk about is a research study in which we looked at, with regard to near-field training simulators, like surgical training simulations or mechanical skills trainers for mechanical engineering students or electrical engineering students, to what extent stereoscopic viewing, that is 3D viewing in VR, and the sense of touch is, to what extent is that important with regard to perception action coordination or fine motor control. This was also accepted as a paper at IEEE VR 2019 and was presented at Osaka last year. So perception action coordination is the circular transfer of information between sensory systems and motor structures. And one needs to be able to perceive things like depth, size, scale, length, width, height, all of these perceptual characteristics in the virtual world as accurately as the real world, so that when they reach out and they want to perform some sort of fine motor action, such as mechanical assembly or placing a manifold on a motor, things like that, in the near field, they should be able to do so with the equivalent amount of motor control that they have in the real world. But in the virtual world, we know that perception action coordination suffers and motor control is not as effective. So to what extent does stereoscopic viewing, that is 3D viewing, and also the sense of touch, help in these kinds of mechanical skills trainers? So on the left, you see a Da Vinci system-based virtual reality mechanical skills trainers that does not have stereoscopic viewing, but it has haptic interfaces. These are devices that provide a sense of touch in virtual reality. And then in the center, you see simulations that we have created as part of the Center for the CAVES project, Center for Workforce Development, in which these are our mechanical skills trainers. And these trainers have stereoscopic viewing, but do not have haptic feedback. Furthermore, on the right is a electrical simulation with a simulated breadboard apparatus to also teach electrical simulation concepts and the fine motor skills with regard to electrical engineering. So there's some related work here that has been conducted in order to study users' affordances and visual and haptic feedback with regard to just the act of reaching. But then there's no work that has examined both the sense of the 3D viewing as well as the virtual sense of touch on motor control. So this is what we were investigating. And furthermore, when you have these haptic interfaces, the workspace with which you can operate a haptic simulation is very small. So as a result, a gain is often applied in simulated activities like surgical training using the haptic manipulator, in which if you move your physical haptic stylus by 1 centimeter, your virtual stylus in the virtual world may actually not move in a congruent fashion, in a one-to-one fashion, but may move in a discrepant fashion such that with gain, it may move 3 centimeters for 1 centimeter of movement in the physical world. And we also wanted to see how that sort of impedes learning and impedes motor control. So we created a replica of a task called the PEG transfer task from the fundamentals of laparoscopic surgery. On the left is the physical task in which surgeons practice with real laparoscopic probes how to move targets from one peg to another. And on the right, you see the virtual replica of this task that we created. And so we created this task. This was my student David's PhD dissertation work. This is the haptic device that we are using in this simulation. And this haptic manipulator has a very short range. It costs around $3,000 or so, and it represents the most advanced interface for a sense of touch. And it provides a sense of touch for a point to a surface collision in the virtual world, so that the collision forces will impede the participant from being able to penetrate the surface in the virtual world. So here are the dimensions of our apparatus in the virtual reality setting with regard to the ring dimensions as well as the pegs. And the task was to move the move the ring from one peg to another. And so here are demonstrations of this. So my student David is picking up a ring in the virtual world using his haptic manipulator, and he's moving it to a destination peg. And then from that initial peg, the new destination is specified in the simulation, and he's got to carefully move this as fast as possible with the minimum number of collisions and as accurately as possible. And in the 3-peg scenario, there's one-to-one movement between the physical stylus in the with this haptic device and the virtual stylus in the virtual world. There's no discrepancy. Or in the 5-peg scenario, with 1 centimeter of movement in the physical world with the haptic stylus, the virtual stylus moves 2 centimeters. So this is a discrepant motion, and we want to study to what extent this affects fine motor performance in virtual training tasks. This discrepant simulation is further exacerbated in the 7-peg scenario. And here you see David picking up a ring, and he's moving it in such a way using the haptic manipulator such that 1 centimeter of movement in the physical world using the haptic manipulator corresponds to 2 centimeters of movement in the virtual world. And so this requires much more fine motor control to overcome this discrepancy. We also created an after-action review simulation such that actions that are performed in the virtual world could be coded through an after-action review in the physical world, and then we can extract these metrics such as completion time, the ring distance, how far the manipulated object moved in the virtual world, the number of collisions that resulted when they performed this task in the presence or absence of stereoscopic viewing, or discrepant motion between the visual proprioceptive and the kinesthetic cues, and also the placement error. That is, how far was the center of the ring from the center of the pegs? So if it was perfectly surrounding, when it dropped on the pegs, was it perfectly surrounding the pegs on all sides, or was it discrepant in some ways? It corresponded to placement error. Some of our research questions was how do haptic feedback and stereoscopic viewing affect perception, action, coordination, and motor control? And does this, if there's any mismatch between visual proprioceptive cues, does it affect motor task performance? And then we also wanted to look at adaptation or calibration over time, do they get better in performing this type of task, fine motor task? So for adaptation, we looked at sets of trials. So each participant received 20 sets of trials in a random order between the 3-peg, 5-peg, and 7-peg scenarios, either in the presence or absence of haptic and stereoscopic viewing. Those were our independent variables. And we looked at, for calibration, we subdivided these 20 trials into sets of 5, and we looked at how these dependent variables changed from one trial set to another. When it came to completion time, we found that there was an effect of haptics as well as the gain scenarios. We found that when haptics was off, the completion time in this fine motor control simulation took much longer as compared to when haptic feedback was on. So although haptics is very expensive to afford in virtual reality interactions, it seems to provide benefits with regard to completing the task quickly, a fine motor task quickly. And then when we looked at trial sets, we found that when haptics was off as well as when haptics was on, that the completion time in the first 5 trials took the longest. But then, however, in the next 3 sets of trials, participants seemed to be well calibrated, and they were able to home in on a particular completion time, depending on the condition, haptics off or haptics on. With regard to the distance that the manipulated object, here in this case the ring, was traversed through this over this fine motor task, we actually found that both when stereo and haptic feedback was off, the ring distance was the largest. So essentially, participants' motor control of the manipulated object took the longest time, whereas when both haptics and stereo was on, which is on the far right side, we found that the manipulated object took the shortest distance to the destination. But however, when either stereoscopic viewing or haptic feedback was on or off, performance was actually equivalent. Likewise, we also, with regard to the distance of the manipulated object, we found that overall, when stereoscopic viewing was off, the distance traversed was longer as compared to when stereoscopic viewing was on. But this difference only happened in the 5-peg and 7-peg scenarios. So when they had congruent visual proprioceptive feedback, which is the 3-peg scenario, there was no significant difference. So when there is incongruence, then the stereoscopic viewing really matters. And there's incongruence between visual proprioceptive and kinesthetic feedback is what we are finding. Also, with regard to ring distance, we found that when stereoscopic viewing was off, participants, the distance that participants could control the manipulated object took a much longer path in the first 5 trials as compared to the next 3 sets of trials. However, when stereoscopic viewing was on, there was no evidence of calibration. They seemed to be already homed in. They already seemed to be well calibrated or well adapted such that ring distance was essentially equivalent across all the trial sets. Finally, number of collisions. This is a very important metric for motor control. We found that there was an effect of haptics as well as separately and an effect of stereo in collisions. So when both haptics and stereo was off, number of collisions was the highest. When they were both on, the number of collisions were the least. However, what was interesting again was that when one or the other was on or off, then performance with regards to number of collisions was equivalent. When we also looked at number of collisions, again, we also found an interaction effect with stereo by the gain scenarios. And here, what we are seeing is that when haptics was off, participants, the number of collisions were overall high, and it seemed to increase with the discrepant motion between the visual, proprioceptive, and kinesthetic cues. So in the 7-peg scenarios, we see that when haptics was off or on, the 7-peg scenarios resulted in the highest gain as compared to the 5-peg and then the 3-peg. So as complexity increases, there seems to be much more collision in virtual reality. It seems to be much more exacerbated when the sense of touch is not there. Finally, with regard to placement error, the effect that we find has to do with stereo, and here 3D viewing seems to be the most important. Participants' accuracy with regard to doing this fine motor, near-field fine motor task is significantly worse when they do not have stereoscopic 3D vision as compared to when they do have stereoscopic 3D vision. So with regard to accuracy, we have shown that stereoscopic viewing plays a very important role, especially in the near field. So our conclusion is this. haptics and stereo seems to be differentially affecting participants' performance characteristics. Haptics has a very strong influence on efficiency, that is, the time it takes to complete the task, while stereoscopic viewing seems to have a strong influence on the economy of motion. The economy of motion is the distance, the path length of the manipulated object as you're moving the manipulated object from one location to another as you're performing this fine motor task. So that seems to be much more longer when stereoscopic viewing is not there as compared to haptics. And task performance seems also to be affected by haptics strongly. So there were less collisions and higher placement accuracy when stereoscopic viewing was there. We found a negative effect of visual haptic discrepancy and user performance. So when I say discrepancy, this is the discrepancy in visual proprioceptive kinesthetic tactile feedback. So if they are all congruent, just like how we experience real-world interaction, then the errors are less. But when they're discrepant, and this could happen due to the fact that there are technological limitations with the haptics hardware, such as the range of motion of the haptic manipulator is so short. So as a result, VR developers may add a gain such that you may move the haptic manipulator by 1 centimeter. The virtual manipulator moves by 2 centimeters. But the one thing we would caution here to the development community is that adding such gain has a detriment on participants' fine motor performance. However, regardless of what sort of situation that they're getting with or without haptics or stereoscopic viewing, we see that calibration is taking place. So users' neurological system intervenes and participants are able to calibrate to that setting and are able to increase with regard to accuracy and precision of the task over 5 to 10 trials. So our recommendations are that in many near-field fine motor haptic simulations, such as robotic-assisted surgery, a gain is added to maximize the haptic workspace. The training module, so any mismatch in visual haptic proprioceptive feedback can degrade efficiency and effectiveness. And in spite of reduced cue situations, participants tend to calibrate. It's the good news with regard to their fine motor coordination. So we recommend application developers to include some brief acclimation or training phase before they actually start introducing them to the fine motor simulation tasks. Our future work involves essentially looking at different display metaphors. So right now, my student David is looking at how large screen stereoscopic displays versus head-mounted displays, two types of display systems in VR affects fine motor coordination, and whether having a view of your virtual hand or having a view of your physical hand via a virtual hand helps with regard to motor control. So that's something that we are looking at as well. So here's my contact information. With that, let me conclude my talk, and I'm glad to take any questions. Thank you for your attention.
Okay, we have a couple of questions that come into the chat room.
Great.
First question, what are your thoughts on industry adopting some of the components of their automotive study to support training their work?
We think VR has great potential. So, we do encourage industry to look at virtual reality and virtual reality systems as a way to provide workforce development training with regard to fine motor tasks in the near field, as well as things like inspections that they may need to learn how to do in using virtual reality modules, or perhaps looking for safety infringements. And we have created modules for these types of domains. And there is much more when it comes to mechanical assembly, electrical circuitry, and so on. And so there's a wide variety of ways in which I think industry can benefit from the use of virtual reality simulations. And virtual reality simulations are very effective for providing educational experiences when the type of content is very well specified. So if there's a standardized approach by which one needs to perform an inspection, or one needs to potentially look for safety infringements, or one needs to do a checklist of items before handling a complex machinery, then virtual reality could be used to essentially provide that training experience for participants to be able to learn those checklists very effectively. And for fine motor manipulation too, like an example of which I showed you here, I think those types of near-field tasks, virtual reality can also be very effective. But therein, it's important to recognize the importance of stereoscopic viewing, motion parallax, and some of these perception action processes that we are so used to in the real world and needs to be correctly developed for virtual reality. So designers of these systems, if they do a good job at replicating these perceptual mechanisms, perceptual motor control mechanisms in virtual reality, then we think that these, when it comes to near-field tasks, bimanual near-field tasks, such as mechanical assembly, VR simulations could be very effective. But generally, VR simulations have the advantage of providing participants with a training experience anytime, anywhere, any number of times, and so it's repeatable. And so that's one of the benefits of VR technology. And many of our learners have some sort of VR system at home, either for gaming purposes or entertainment. So those platforms could also be leveraged towards training anytime, anywhere.
Okay, we have had a couple of questions coming to the chat. Anyone would like to take this opportunity to unmute the microphone and would like to speak out, please do so.
Oh, Zach, I think your sound is a little off, so I think your sound is a little off, Zach, so I can read that next question if that was what what you're doing.
So I was giving people the opportunity to speak up if they want to versus using the chat window.
Okay, I'm not sure. Anyway, I'm going to ask you the next question. So you mentioned in the workspace about the haptic interface and it being small, and the haptic interface peg transfer example, where your student David was moving the device from left to right while the screen showed close to far movement. Is there a disconnect there, or could the screen be moved to show the right to left movement?
So in the demonstration video, it may have been confusing to see what is the directionality of motion that we are simulating. Both in the physical world as well as in the virtual world, the directionality of motion was the same in our studies. So the participant could move the stylus forward and backward, and in the screen, which is directly in front of them, they will see the stylus also moving closer to and further away from them along the optical axis, along the axis of viewing. So in that sense, Rebecca, it was exactly the same direction of motion, but it also opens up an interesting question of what happens if you actually change the direction of motion in the virtual world as compared to the physical world. And so we have not conducted that study, and that's a very interesting idea. If you have, that's oftentimes possible, because sometimes with regard to fine motor types of tasks, I have seen simulations in which you're performing the task on a tabletop using the mouse, and your mouse movements are simulated on the screen that is 90 degrees to the tabletop. So you're performing motions on one plane, and the cursor of the mouse is on a different plane. This is something that we are used to from day-to-day interactions with computing systems. But if it happens in virtual reality, can participants have good fine motor control? We don't know. Great question.
Okay, thank you. Just one other was the iVRNote, the online remote platform that
Yes.
you highlighted. What other tools is your team thinking about incorporating into that iVRNote classroom? And yeah, I'll let you answer that.
Sorry. So currently we have focused our efforts on note taking in this in that first year, and this year, continuing that project, we're actually thinking about sketching and art. So if they are engineering students, then they need to be able to perform some sketches to create blueprints of some of these complex machinery, or if they're architects, they need to create blueprints of buildings. To what extent do they have good fine motor control when they're performing these kinds of sketching tasks? And this is not sketching for entertainment, such as the tilt brush application that some of the viewers may be familiar with that exists in virtual reality with the HTC Vive platform. But this is very precise, fine drawings that engineers have to make of various parts and objects and environments. So can we provide some interaction metaphors that facilitates that? Maybe rulers and other types of devices that they could call on demand with which they can create these architectural or engineering blueprints. So that's our current work in progress.
Okay. Any other questions from the group that you can put
I just saw a question that just came up.
Okay.
And the question was, do you have any business opportunities where the iVRNote is being adopted? So currently, my collaborators and I, having published this work, we are now thinking about potentially copywriting the system. So, we haven't thought of working with any industry partners to release it yet. But however, our publication does show the implementation details, if you like, or the design details of our iVR system note-taking interaction metaphors. So as a scientist, I'm really interested in innovating new interaction techniques and studying how people like or dislike these interaction techniques, what works, what doesn't work in the virtual reality realm, and pushing the boundaries of the science in VR, while simultaneously meeting the educational and career goals of our students with regard to their master's, PhD thesis, and their future aspirations of becoming scientists and academics and researchers. So we haven't really focused on the entrepreneurial aspect of these, but a company could look at our publications, and good software engineers could easily replicate some of our techniques. So we have provided that as a contribution to the general public, while considering potentially, copywriting our software.
Okay, thank you for that. I don't think we have any additional questions unless anyone wants to type one in while I'm giving the last bit of information about the webinar, and we'll be happy to ask that. But we have just a short survey that we would like for everyone to take. And we're going to put that in the chat window, and we'll also be able to send that to you following the webinar. So just it's very brief, and if you would be able to just answer these short questions just to give us a better idea of how everything went today, and then any follow-up questions that you might think of that we could talk with Dr. Babu about and then get answers to you. I'm happy to do that, and as you see, he's provided his email address and contact information for you here. So a big thanks to Dr. Babu for doing this presentation and for his continued work with our center, the Center for Workforce Development, and again, all of the wonderful graduate students that he is producing that are helping the center to be able to develop products that help our partners. So thanks everyone for your time and attention today, and this will conclude the webinar. Thank you.
Happy to be here.